So as I said, coupled cluster theory, but using Monte Carlo methods. So this is work that has already been presented in the literature. So how to use Monte Carlo random number sampling to basically propagate and obtain a compressed representation of the coupled cluster wave function. So one algorithm that exists parameterizes the wave function in terms of pseudo time-dependent cluster operator, and then propagates the coupled cluster equations in the pseudo time to obtain a compressed representation of the wave function. So how that works is that for any at any given time, we select one cluster operator and collapse it down to a determinant, then apply the Hamiltonian to obtain a determinant that is either a single or a double excitation with respect to the determinant that we have selected. This is called birth. We apply diagonal corrections to this birth process through a death cloning step that might duplicate or eliminate the given determinant. And finally, we check the sign of this generated determinant and annihilate any determinant that appears with opposite signs. This kind of propagation can be really effective to compress the information in the wave function. However, the problem that appears is that if we run this kind of simulation on systems of non-interacting atoms, for example, in this case beryllium atoms, the memory cost is a measure of size extensivity, and it should be the cost per replica should be constant. But instead what we see is that this is not true, and this precludes the use of these methods for large systems because the memory cost can become extremely large, and even though we can distribute over multiple nodes and in a way amortize this memory cost, it becomes soon untenable. And the reason for this, sorry, I'm going back to the previous slide, is that we are using in CCMC the unlinked formulation coupled cluster. So even though the method is size extensive order by order in the coupled cluster expansion, there will be terms that are non-size extensive that we will need to sample during the propagation. And these terms will take up space. And even though they do not contribute to the final energy because they cancel out exactly, we still need to carry them around. Okay, so the problem is well identified. And the solution is also well known, at least in our community, and it is to use the similarly transformed Hamiltonian, H bar. And the problem in a random realization coupled cluster is that sampling the Baker-Campbell of expansion is extremely difficult because there are a lot of coupled terms, and the simple propagation that I showed at the beginning cannot be applied straightforwardly. So what we did is to look again at this kind of parameterization, and then rather than expand H bar into the application of the exponential operator on the reference determinant, to carry it around as that and expand the red term that I have highlighted as a finite series of diagrams. So consider it as an integral, and realizing that that integral is just a sum of a finite number of terms that can be expressed in a very algebraically convenient way. And with this in mind, we can do an important sampling to build the diagrams on the fly during the propagation, and then apply a stochastic rounding of the amplitudes that we select in this important sampling algorithm, such that if there's any amplitude that in absolute value is less than a given threshold, we throw it away. Otherwise, we store it. So how does this work a bit more concretely? So we want to sample terms from this highlighted red term in the equation. So first of all, we start by applying e to the t on the reference determinant. And this means we only have a limited number of options because we know that this truncation, this expansion truncates exactly. And within each truncated term, we also have a limited number of terms that can be selected. So a limited number of combinations of cluster operators that will lead to something that is non-zero. Once we have selected that, and that corresponds to drawing the lower part of the diagram, we can select a Hamiltonian vertex, and this is the upper part of the diagram. And once we have these two upper and lower parts, there's a limited number of ways we can contract them together. With the contraction hand, we can select which summation indices for the contracted vertices and which indices will be the external vertices. And concretely, what this does is select one specific diagram, which will correspond to one specific amplitude, and this amplitude will be stored in our wave function representation, but only if its absolute value is above a preset threshold, which gives us the stochastic sparsifying of the cluster operator. Okay, with this hand, this was the original graph, and with our new method, we do get the memory cost down, and most importantly, it behaves as it should for non-interacting systems. Okay, so this is work in collaboration with people in the UK, so Charlie Scott in London and Alex Tom in Cambridge, and of course Crawford at Virginia Tech. And what I've shown is just part of what we've done so far in the interest of time. But we have extended this method to also use a factorized form of the coupled cluster equation, so that we can not only bring down the memory cost, but also the CPU cost. And with this, I stop.